Hello, my name is Brian Schultz, and today I'll be presenting the research paper Exploiting a Thermal Side Channel for Power Attacks in Multi-Tenant Data Centers. This paper was originally published by Mohammad Islam, Shaolei, and Adam Wierman at the conference Computer and Communications Security Conference in the fall of 2017 in Dallas, Texas. Today I'll be discussing some of the history as it relates to power and in the context of data centers. And we'll be looking at data centers in detail, discuss how to exploit a thermal side channel and various strategies for attacking it, how to defend from these attacks, and any experimental results such as attack effectiveness and costs associated with these attacks and defenses. But first off, what is a power attack and what is a thermal side channel? In data centers, you have a certain power capacity. A power attack occurs when you try to overload the power capacity by causing a power draw, an increase in the power draw in the system. So a successful power attack occurs when the current active power plus the additional attack power is greater than the power capacity as a whole. This will lead to something called a power emergency, and a power emergency could lead to a circuit breaker being tripped, and then that would cause an outage in the data center as a whole. Now, a thermal side channel is essentially heat flowing from one server to another. Whenever a server is processing a heavy load, it requires more power to run this load, and that power will cause heat to emit from the server. Now, another server can take in this heat from the server air intake point. So the heat from the first server being produced will travel over some space and time and reach the other server. This can be detected by temperature sensors on the air intake of the other servers, and it's also modelable by using fluid dynamics to model the flow of this heat throughout the data center. Most studies that have been performed up until the publishing of this paper have focused around the power and cooling efficiency of these data center systems. So really they're just trying to eke out as much performance and save as much cost as they possibly can with these systems. As far as data centers themselves go, there's really two types. There's private data centers and multi-tenant data centers. We'll discuss more about multi-tenant data centers in the next slide and why these are susceptible to power attacks. But first, why are private data centers not susceptible? So private data centers are usually just a single tenant, such as Google, Facebook, and Twitter, and they own these whole data centers, and they fully control the hardware and all the resource utilization. So they can limit the amount of power being drawn by every server and prevent any successful power attack from happening, even if they allow other customers to put VMs on their systems. And really, their main goal is not necessarily to make as much money from the power in the data center as they can, but to achieve as close to 100% of their power capacity as possible to make this data center more efficient. Now, who would want to attack these and perform a power attack? Well, it's possible to have state actors trying to disrupt some services and disrupt the economy. And it's also possible that one of the tenants is a competing data center itself. So they're trying to disrupt the operations of the data center and cause some consequences that result in monetary loss and customer loss for the data center that the power attack happens on. Let's go back and take a look a little bit deeper into multi-tenant data centers and why they are susceptible to power attacks. The typical setup for tenants within a multi-tenant data center involves contractual agreements. And these contracts will allow a tenant to draw a certain amount of power from themselves. Now, they cannot always draw this full power. It's typically limited to about 80% power draw per month of their total capacity, and if they go over a certain amount, then it's possible that these tenants could be evicted. Why do they do 80% per month? That's because the multi-tenant data center is trying to make some money, so they will oversubscribe their total power capacity by typically about 120% or so. It could be more, it could be less, but basically they're hoping that all of their tenants won't be drawing at full capacity at the same time. This can still happen, and this can lead to outages and power issues. So this contract and this oversubscription is what causes these multi-tenant data centers to be susceptible to power attacks. Going a little bit further, multi-tenant data centers are tiered, and these tiers are provided by various standards and certifications, such as the Uptime Institute certification and a standard called the TIA 942 standard. There are 4 different tiers, and these are based on various redundancy requirements for the power and cooling systems and uptime percentages throughout the year. We'll dive into a little bit of a Tier 4 data center's hypothetical power system. As you can see on the far left, there are 2 utilities supplying power to the data center and also 2 generators supplying power as well. All of these systems feed into the ATS, which stands for an automatic transfer switch. And what that does is, let's say one of these power sources goes down, it'll automatically switch over to the other power source and start pushing that power on forward down the line. That ATS then feeds into a UPS system, and a UPS you could really think of as a big battery. It'll take in this high voltage power from the ATS, which is pretty much direct from the utility or the generator, and it's going to condition that power and store it a little bit and push it on down the line to what's called a PDU. PDU stands for Power Distribution Unit, and there's going to be multiple levels and tiers of these things on down the line. What a power distribution unit does is it's going to take this higher voltage and conditioned current and step down that voltage and push it on down the line. So you can see why these multiple tiers of PDUs happen, because we need to keep stepping this power on down all the way until the point where it hits the rack PDU, and the rack PDU will supply power directly to the servers. Notice at each stage of this power system is redundancy. That's what makes a Tier 4 a Tier 4. It has 2N or better redundancy. So there's 2 of everything at every stage. 2 lines, 2 UPS systems, 2 PDUs, whatever, what have you. It's got 2 of it all. Let's also take a look at a typical cooling system for a data center, because this will show you intuitively how a thermal side channel will form. On the ends of this diagram we see a CRAW, which is a computer room air handler, and this essentially works by throwing hot air over top of chilled water, therefore cooling it down. This chilled water gets provided by an external chilled water plant. So you can see it alternates hot aisle, as denoted by the red and orangish arrows, and cold aisle is denoted by the blue arrows. So it goes hot, cold, hot, cold, hot, cold. These are how most data centers are aligned. So the servers will output their air, their hot air, into the hot aisle, and they'll suck in air from the cold aisle, and that air gets supplied from the ground via perforated floor tiles typically. So this hot air that the server is pushing out is going to get sucked back in by the craw and it's going to travel over this space over into the craw and create this flow. As you can see by the arrows labeled 1, some of this air isn't going to make it to the craw. In fact, it's going to get recirculated back into the cold air intakes for some of the other servers. This is the thermal side channel that forms, and this is the measurable heat that you can grab from some of the servers. We have enough information, background info, and context that we can move into the actual attack itself. Let's start off by talking about what the attacker cannot do. The attacker cannot trip their own circuit breaker on their rack. If they trip their rack circuit breaker, then their attack fails because they can no longer draw power via their system. We're also going to say that the attacker cannot be evicted from the data center because they're trying to continue to perform this attack and cause outages and cause damage monetarily or physically to the server. Now, some of the things that the attacker can do or they can know are the shared power capacity and the total power capacity of the data center. That's usually part of the contract, so they know exactly how much they can draw and how much power the data center can supply. They can also take out multiple contracts under pseudonyms looking like different tenants, so that they could get set up in different areas of the data center and draw more or less power from the data center as much as they want, really. They can also arbitrarily generate load on the CPU in order to create power draw however they want. And this could just be done with old servers and just do some number crunching and they're going to create a power draw. It's also possible, we're going to ignore this in this study, but it's also possible that you could exploit a co-located tenant's public services and cause those tenants to draw extra power. We also need to be able to, as the attacker, conceal temperature sensors on the server air intakes. This is going to measure the thermal side channel, and it's also going to measure the output temperature of the craws, or the cooling units. You can put these temperature sensors at the bottom of the rack to get the best measure of the craw as you possibly can. Now finally, the last thing we need to do, and the most complicated thing, is going to be the performing computational fluid dynamics. Some things that we need to note here: you can actually walk the data center and get an idea of the layout. So where are these craws located? Where are the servers located? How are they aligned? What's the approximate distances and approximately how many servers exist in this data center? Approximations are fine. And we're going to plug this into something like AutoCAD CFG in this case and create a fluid model for the heat flow throughout the data center. These are the steps that it takes to perform a thermal side channel power attack. We're going to take the information that we've gathered from the flow analysis and the temperature readings themselves, and we're going to pass this through what's called a Kalman filter. We'll get into this Kalman filter a little more next, but then what that's going to give us is an approximation of the heat for every server in the data center, and with the approximation of heat for each server, we can approximate the amount of power being drawn by these servers at that time. Then once we have these approximate power estimations, we're going to follow a plan of attack, or the attack state machine. And this is going to tell us when to wait, when to attack, and when to stop attacking. And when the state machine says attack, we're going to ramp up power by increasing the CPU workload on our machines. Let's talk a little bit more about the Kalman filter itself. In the interest of time, I'm not going to dive deeply into the math. I'm going to try to give you an intuitive understanding of what the Kalman filter lets us do. And you can imagine that the the thing that we're actually reading and sensing is the heat, and there's a hidden state as a result of this heat, which is the amount of power being used. It correlates to the amount of heat being produced. So what a Kalman filter lets us do is approximate this hidden state from the heat output. Now the actual power use itself is very random. We don't know when a co-located tenant's or another tenant's power usage is going to be high. It could be due to various services being activated at a certain time. We're just not sure it's going to happen. But what we do know is that we know our own power use, what our own static power use is, and how much power we can produce. In order to prevent this computational explosion, what we can do is just do a zonal approximation for the power. So we estimate the heat and the power output for various regions in the data center. Let's just say there's 4 regions, like a north, south, east, west region, and we're going to do approximations for each of these zones. This is what the Kalman filter will help us do. Now, once we have these power estimations, we need to follow some rules of engagement, if you will, in order to not get evicted from our data center. This is the attack state machine here. So let's start at the beginning of the state machine and look at the idle state. I'm going to start here, and the number 2 labeled arrow is going to be when the power estimated is greater than the power threshold that we have set. So once that happens, we're going to move into the wait state, and wait for that t-wait amount of time. If the power estimated ever goes below that threshold, we're going to go back to the idle state. But let's say that the power estimated stays over top of the power threshold and t-wait expires. Well, now we're going to move into the attack, following the arrow into the attack state. Why do we do that? Well, we don't want to just start attacking whenever the power draw is actually just a transient power draw. We want that power draw to happen for a certain amount of time so that we know it's going to be sustained. So now we're in the attack state, and we're going to start our attack, ramp up all our servers, and start drawing power as much as we can. And we're going to do that for a certain amount of time. Once that amount of time is done, now we're going to move over into the hold state and just wait for that amount of hold time. And then after that time is up, we move into the idle. We set the attack times and the hold times to correspond to our individual contract. We have our attack, we have our calculations, and now let's actually evaluate how effective is this attack and this strategy. There are 2 definitions I'm going to give you here. For one, the first one is true positive. The true positive is the percent of actual attack opportunities captured. So if there is a attack opportunity where we could successfully overload the power system, if we capture that attack opportunity, then that is a true positive, and that proportion is the true positive percent. There's also precision, which is based on the percent of successful attacks launched. So let's say we launch 100 attacks and 50 of them are successful. So a successful attack is, again, we can actually overload the power capacity. Then that would be a 50% precision rate. If we take a look at this top graph here, this shows the heat matrices for every sensor. So the rows correspond to the temperature sensors, and each of the columns, they look like little lines because there's so many of them, are one of the 840 other servers for which we're trying to actually estimate the temperature. Now, anything that's more red is going to be an overestimation, and anything that's more blue is going to be an underestimation of the actual values of the temperature for the servers. So green here is good. That's a solid, that is a 0% error for that. We get about a 20% error for this, but this is just for estimating the heat. What we're really trying to do is estimate the amount of power draw, and that's this graph down here at the bottom. So you can see this black line, this black dotted line going straight horizontally across the graph. That's going to be the total power capacity for the data center. The blue squiggly line is going to be the actual power being drawn in the data center at the time, and the red dotted squiggly line is going to be our estimation of that power draw. So you can see that line, the estimation line, is fairly tight to the actual power being used in the data center, which is fantastic. And as that blue line gets closer and the red line gets closer to that power capacity, that's going to present attack opportunities to us the closer it gets. So the little red highlighted areas that are the vertical areas, that's going to be our attack opportunities. And what that is when we can draw all of our power, start just drawing as much power as we possibly can, when that will exceed the total power capacity for the data center, that's going to be an attack opportunity. So you see those red vertical lines in some of these shaded regions? That's going to be when we actually perform the power attack, and that's a successful power attack happening. That's the one where we actually pull the power draw in the whole data center over the total power capacity. There's also the green lines that you can see going vertically. Those are going to be unsuccessful power attacks. So when we draw as much power as we can, but we cannot surpass the total power capacity for the system. And you see it's about a 50%, a little bit better than 50%, our attacks are successful. Now, how do we defend against these attacks? We need to degrade this side channel. And what I mean by degrade is try to reduce the amount of information that you can glean from the thermal side channel. There's a few ways you can try to do this. You can randomize the cooling temperature, which basically any of the temperature coming out from the craw is going to be either 60 degrees Fahrenheit all the way down to 30 degrees Fahrenheit, and somewhere in between is going to fluctuate. You could also randomize the airflow itself, so this would help to change the flow model that we calculated within the data center. It's also possible to increase redundancy by just buying more equipment and throwing that down. You could also do heat containment, such as blocking off the cold aisles, or blocking or creating a system that will suck the heat directly from the hot aisles and place it into the craws or the cracks. Now, which of these defense strategies is going to be most effective? It's going to be heat containment, and we'll talk about why. As you can see at this graph down here, this is the true positive and precision rate for the various types of defensive strategies. We have the baseline, so no defensive strategy, random supply, and on down to 99% heat containment. So if we try to do any of the random supply or random airflow, this is going to be relatively expensive. You're going to have to get new equipment and install that at your location and try to manage this randomness in some way, and that's just going to be pricey. One of the other methods was to stop oversubscribing. That's going to lead to a loss of income, so we're just not going to consider that for multi-tenant data center. And you can also provide more redundancy. That's expensive. We need to buy more equipment as well, so that's very pricey. The winner here is heat containment, because it's relatively cheap to install some form of heat containment, such as blocking off the cold air aisles from allowing the thermal side channel to enter into the cold aisles. And after the installation is done, there's really no management that you have to do beyond just physically blocking off these channels. So the winner is clear. Heat containment can help prevent this thermal side channel. Now we know that this attack is possible and feasible, but is it worth it to the attacker to perform this attack? Well, yes, it is. It's relatively cheap for the attacker to perform this attack. All they need is to pay for the co-location costs within the data center and they can use relatively cheap equipment to draw power. It's very easy to get any sort of equipment and pull as much power as you can possibly want. And as far as the cost of the data center, it's very high, because you cause an outage for the data center, they lose money by that. And if you cause enough outages, the data center themselves could potentially drop tier classifications, which would mean that they have to charge less for co-location within their data center because they're a lower tier. So you're causing more outages and reducing their uptime, which affects their tier classification. It also costs money to the tenants, because any outage that they have is going to be an outage in their services. So for example, Delta Airlines, in one case study, they had an outage at their data center, and it cost them $150 million for 5 hours of downtime at their data center. In conclusion, the thermal side channel exists, and it's possible to exploit this thermal side channel and perform a successful power attack on the data center. The best defense that you could possibly do is heat containment. If you can contain up to 99% of the heat from the hot aisles in your data center, then that's going to be a very effective defense against power attacks such as this. So that's it. Thank you very much for watching my presentation. I would like to thank the authors for creating this research paper, and I'd like to thank iStock for that free shield image that it provided. Thank you to the Uptime Institute and TIA for their logos, and also thank you again to the authors for the graphs that you saw within the paper. That's all for my presentation. Thanks again for listening.